Hello, everyone. I'm Krishnamova, and I'll be presenting this paper called Adaptive Perception Control for Aerial Robots with Twin Delayed DDPG. My co-authors are Kunjan Theodore Joseph, Dr. Samal, Dr. Wolf, and Dr. Petla. And we are from University of Nebraska-Lincoln. Convolutional neural networks brings a trade-off of latency versus accuracy. A high accuracy network tend to have a high latency, and a low latency network suffer from low accuracy. Either one of these are not sufficient to satisfy the requirements of the plant. Certain times, the plant requires a confident input, and certain other times, it requires a faster inferences. So either one of these could not satisfy the requirements of the plant. That is the reason why we have implemented an adaptive perception control which adapts in accordance with the nature of the environment to satisfy the requirements of the controller. So that is the reason why we have implemented an adaptive perception control, a perception module which changes its latency and accuracy configuration in accordance with the requirements of the controller. We have tested our approach in an US tracking scenario in which Bravo, which moves in its path, which is unknown to alpha. The goal of alpha is to detect the Bravo and track its trajectory. This can be achieved only through the perception, which is aware of controller's requirements, and the controller, which is mindful of perception's limitations. The first step in implementing such kind of a system is that creating an adaptive CNN, a convolutional neural network which can provide different configurations of latency and accuracies. Here, the color represents whether the network is lightweight or not. If we look closely at the convolutional neural network, especially the neurons, we can see that it has a number of filters. We can achieve a different configurations of latency and accuracy of the network by turning on and off these filters. To quantify the importance of the filter, we have created a measure called the impact value. The impact value of the filter is the combination of the mean absolute sum of the filter, which tells how good the filter is in extracting the feature points, and the back propagated gradient, which tells us that how important the filter is in its inference. By setting an impact threshold and turning off all the filters below the impact value and keeping the remaining filters, through that, we can achieve an adaptive CNN which can provide different configurations of latency and accuracy. One issue in turning off the filters is that oftentimes the accuracy falls to single digits. So that's the reason why we have incorporated a randomized regular parameter while we're training the network. This parameter makes sure that no one filter is responsible for extracting certain distinct feature points, and at the same time making sure that the filter values falls under different spectrum of values. In that way, we can achieve a convolutional neural network which can provide different configurations of latency and accuracy. Here you can see the results of that. The existing deep learning libraries such as TensorFlow and PyTorch, typically when we turn off the filters or prune the network, they replace the filter values with zeros. In such cases, you can see a decrease in accuracy, but a decrease in latency could not be observed because the computations are still happening. So that is the reason why we have modified the C code of the darknet, which is the backbone to YOLO network, to achieve the latency effect. You can see the results on this picture. As we are increasing the impact threshold, you can see that the accuracy of the network is going down, and at the same time, the latency of the network is also going down. Through this way, from one convolutional neural network, we can achieve different configurations of latency and accuracy. You can see our visualization results here. That is, with impact threshold of 0.0, the CNN is able to detect all the frames, whereas with 0.02, it failed to detect certain frames as its accuracy is decreasing. To create the perception control to provide the impact threshold, we have used the reinforcement learning. The significant reason is that in autonomous systems, the frames are continuous, in which case, if the CNN fails to detect the object in the current frame, there is high chances that the CNN fails in the next frame as well because all the frames are continuous. Having less feature points in the current frame contribute towards having less feature points in the next frame as well. Moreover, when UAV flies, typically they rotate as they fly, and CNNs are not rotational invariant, so when an UAV is exhibiting certain kind of a maneuvers, there is a chance that there will be a continuous failures. You can see this result in this plot where we have the detections and as well as failures and detections and failures, in which case you can observe that the failures are not coming alone as they're coming along with other failures. Same for detections as well. In the formulation of the perception error as a Markovian gives the time for the adaptive CNN to look this one and adjust its filter to detect the object in the next frame. To design the perception control, we have used the state-of-art reinforcement learning algorithm called the TD3, which is Twin Delayed DDPG. The TD3 has an actor model and two critics, and an actor target and two critics. The reward function contains the perception's accuracy factor and latency factor, which is RPT and RLT. The perception factor tries to give the best perception inferences, so it tries to use all the filters of the CNN. As you can see that its reward is tends to 0 when it uses all the filters. When it starts discarding the filters, the reward is going to be negative. On the other hand, the latency factor is inversely proportional to the Manhattan distance between alpha and Bravo. When alpha is able to track the target well, their Manhattan distance is going to be low. In that case, latency factor tend to discard the filters. So the impact threshold will be decided by the algorithm based on the balance between the perception factor and latency factor. You can see the results of the perception control algorithm training in this picture. It took around 200 episodes for the training to be completed. After 100 epochs, the training starts stabilizing. It has a little bit of oscillation. It's because the positive reward in the perception factor tends to contribute towards the negative reward in the latency factor and vice versa. And after 200 episodes, you can see that the training starts stabilizing, after which point the training got discarded. The overall system block diagram can be seen here. Alpha takes picture through its camera, which will be given to the perception module. The convolutional neural network runs for the inference, and these image coordinates will be passed both to the TD3 PC and as well as image to world pose conversion. So the TD3 control takes the image pose through which it can get the Manhattan distance and as well as if the frame has a detection or not. Based on these two factors, it tends to provide the impact threshold for the next time step to perform the filter activation or deactivation. And the image coordinates will be used to convert into the world coordinate system, which will be given to the LQR. And the LQR control provides the control input, which will be given to the flight controller of Alpha. You can see the tracking results in this plot, and we compared the proposed approach with two baseline approaches, which is HLHA, high latency, high accuracy, which is the tiny YOLO V3 network, and low latency, low accuracy network, which is tiny YOLO V3 network with 75% of its filters, and the proposed approach, which has a dynamic number of filters. You can observe that the proposed approach has less deviation. After that, HLHA, and after that, LLLA. And here you can observe the RMSE of the alpha's acceleration to Bravo's acceleration. You can see here is that the proposed approach and HLHA has a similar performance, and LLLA has a worse performance. In addition to that, we have also conducted 4 different trials for our experiments, and the results can be observed here. The Euclidean distance, you can see that the proposed and HLHA has almost similar performance in tracking the Bravo, and LLLA has a worse performance. The main reason for that is that LLLA has a problems in detecting the target because of its low accuracy. And you can observe here the RMSE of alpha's acceleration to Bravo's acceleration, in which case you can again see that LLLA has the worst performance, and the proposed and baseline has a similar performance in tracking the Bravo. In this plot, you can see the number of active convolutional filters over the flight. HLHA and LLLA has a fixed number of convolutional filters, and the proposed has a dynamic number of filters. You can observe that HLHA has the most number of convolution filters compared to other two methods, and LLLA has a second place, and proposed has the less number of convolutional filters compared to other two approaches. It can emphasize that the proposed approach is not only good at tracking the target, but also with a less number of convolutional filters as possible. On the other hand, LLLA has less number of convolution filters than HLHA, but its tracking is not very good. And HLHA has a good tracking, but the problem is that it has used many number of convolution filters, which means a lot of computations are happening over the flight. This can emphasize the advantage of proposed approach. So overall, we have implemented an adaptive perception control by implementing an adaptive convolutional neural network by modifying the darknet C code of YOLO, and we have implemented our perception control with a state-of-art reinforcement learning algorithm. We have tested our approach with AirSim simulator, and the results emphasize that the proposed approach is good at tracking at the same time using less number of convolution filters compared to the baseline approaches. Thank you very much for listening, and if you have any questions, please do not hesitate to reach us. Thank you.